Kia ora and welcome to this video on question 3 of the 2013 Scholl Calc exam. Interestingly, in this paper, question 2 involved some unfamiliar functions and notation, and question 3a here continues with that vibe and talks about even and odd functions, possibly slightly more familiar to you because your teachers might have used that language. Talks about polynomials. Well, okay, we should know what polynomials are in a calc course, and then it asks us in part II to prove that an even function differentiates to an odd function. Well, that's quite a sneaky proof. We'll look at that. And part B requires us to take a product of two functions and differentiate it 3 times. So we're going to get into some intense algebra for that one, but it's definitely a doable question. Alrighty, first part. I'm going to play around with Desmos for a little bit, just to have a look at a few functions that are even and odd. We're told a function is even if f of minus x is the same as f of x for all x. So if we substitute, for example, 5 in as for x, then the function value at 5 will be the same as the function value at minus 5. Think about what types of functions that could look like. Odd is very similar, but a bit different. If you sub in negative x into the function, you will get the minus of if you just sub in positive x. So again, thinking of that example of 5, the function value of 5 will be the opposite of the function value at minus 5. So let's just have a look at Desmos. The first one that comes to mind is just your basic parabola graph. This one here is an even graph. If we look at x equals a, for example, maybe x equals a doesn't like me to do that. Okay, we'll just go 5 again. X equals 5. Then the y value there is 25. That's exactly the same as the y value at negative 5. So it's an even function. It has symmetry in the y-axis. X cubed is the most simple polynomial. Actually, no, f of equals x is. F of x equals x. But x cubed, that's an odd function. Let's drop our x value down to a bit lower so it's on my screen. X equals 2 gives a y value of 8. X equals minus 2 gives a y value of negative 8. And it's true for all values of x, that you get this rotational symmetry around the origin, 180-degree rotational symmetry. Okay, now if I take x squared, so we go back to the even function, and I add 32, well that's also even, x squared. If I add on another even function, such as x to the 4, even plus even is even in terms of functions. It's also true in terms of numbers. If you take an even number and add an even number, you get an even number. So we still get that symmetry. Think of trig functions. Cos x. Cosine x is an even function. It's got that symmetry. Whatever x value I take on the right hand side, so for example x equals 2, the y value at x equals negative 2 is exactly the same. And so if I add x squared, an even function, the parabola, if I add that to the cosine function, I will still have an even function. Okay, so if you add even with even, you get even. Similarly, if I take y equals x, which is an odd function, and I add another odd function, and this is where it differs a bit, because in numbers, if I take an odd number and I add an odd number, I get an odd number. No, gosh, I get an even number. That's terrible maths. Like 3 plus 5 is 8. But in function land, if I take an odd function and I add another odd function, I still have an odd function. See here, at x equals 2, my y value is 2.909. At x equals minus 2, my y value is negative 2.909. Okay, so that's just a basic understanding of what odd and even functions are. There's some symmetry properties. Now for the first part, we're just talking about polynomials. Describe which polynomials are even and which are odd. So what we need to say is polynomials that are even only have even powers. So e.g. y equals x squared, y equals x to the 4, but in general, and this was important, they made a note of this in the mark schedule, in general, a polynomial a0 plus a2x squared plus a4x4 upwards, so it can have the even terms in it, but it can't have any odd terms. And the reason for that is p of x, actually no, sorry, we want p of negative x. What happens when we substitute negative x into this polynomial? A0 is a constant, x squared, well, we get negative x squared, x to the 4, we'll get negative x to the 4. But of course, when you take a negative number and you power it, the negative has no effect. And that just equals p of x. So that there is an even polynomial. An odd polynomial only has odd terms. For example, can't have the constant, because if it has a constant then it won't have that rotational symmetry, and a constant is a power of 0, so in this definition we're actually saying that 0 is even. We can have a1x plus a3x cubed plus a5x to the 5 upwards. Just also a quick mention as to why they've used this notation for the coefficients, a0, a2, a4 and so on, rather than a, b, c, d, e. Of course you only have 26 letters in the alphabet, but in this notation we can assign the coefficient to the power of the term, and there's an infinite number of numbers, so it's a bit easier to write out all of the coefficients. Okay, the second part. Suppose that g is any even differentiable function. G is an even differentiable function. Not necessarily a polynomial. Use a limit definition of the derivative to prove that the derivative is an odd function. Okay, so as an example, e.g. We start off with y is equal to x squared. When we diff it, we get y dash is equal to 2x, so we go from an even power to an odd power. Even, now odd. Or the trig one that I gave you, y equals equal to cosine of x, well, that's a even function. If we diff it, we go to minus sine x, which is an odd function. But this is asking us to prove in general that that is the case. Okay, so if we take the definition of the derivative, if you haven't seen an earlier video where I explain this, we've got some function that's even. So let's just draw an example of one. And this is some point x, and this is x plus h, where h is small. Then the derivative of g is going to be found by taking the rise and dividing by the run. Gradient between 2 points is rise over run. So we've got g of x plus h minus g of x, all divided by h. And of course we want h to be small, because if we take 2 points that are really far apart, then the gradient of the line between those points is not going to equal to the gradient of the tangent at all. So we make limit as h goes to 0. So that there is the definition of the derivative, often called differentiation by first principles. And we need to prove that the derivative of g, starting as an even function, the derivative is an odd function. Okay, so just copy that down to the next page because I'm going to need it. Alrighty, now if it's odd, if the derivative is an odd function, then what we actually want to find is g dash of minus x and prove that it's the negative of g dash of x. Okay, they should come out as opposites of one another if it's an odd function. So let's find the derivative of negative x. Well, that's just going to be the same limit, but wherever there's an x, we make it a negative x. We know that g is an even function, so we know that g is even, so g of x is equal to g of minus x. And so we can flip this stuff around and it would be the same. So that's going to be equal to g of h minus x, take away g of x over h. Now they do something sort of slightly weird in the mark schedule here, because you still want to use the definition of the derivative, because we want this to come out with negative g dash of x here. So personally, the way that I solved this problem, I worked backwards. I found g dash of x and took the negative of it, and then met in the middle. What they've done in the mark schedule is changed the notation around a little bit. They've said consider k is equal to negative h, because I didn't flip, my bad. I didn't even flip this one around. Like I was telling myself I just wrote them in a different order. G of x equals g of minus x, so that's why I've gone from here to here. But I needed to take the minus of the term in the other one, so I had x minus h. That's better. I just wrote them in a different order. So what they're doing is the k is equal to minus h means that this dude here can be k, and this dude here can be minus k. And the reason for that is now it looks like the definition of the derivative, because the h here is an arbitrary letter chosen. And because it's got a plus in there, it's similar. And also, when k goes to 0, h will go to 0. K is equal to negative h. If we make k 0, h will be 0. And lastly, the way that limit laws work, limits are similar to derivatives, similar to integrals, similar to equations, where you can pull constants out the front of them. So we've got a constant of minus 1 down the denominator. We can pull that out the front. And all that is on the in this quotient here is g dash of x. K is, like I said, an arbitrary letter to choose. So we've got here minus g dash of x. So we started off with g dash of minus x, and we've proven that it's minus g dash of positive x. So therefore, g dash is an odd function. If you start with an even function and differentiate it, you end up having an odd function. That was quite tricky. Often the proof side of scholarship is difficult. And actually, the easier the proof, I find sometimes the more difficult it is to prove it. Because little tricks like what we did there, switching the letters around and making substitutions, those are sneaky little tricks that, if we don't notice them, inhibit us from solving it. But the first part of it, the polynomial stuff, was actually fairly reasonable. And this next question, part B, is a reasonable scholarship problem. It is difficult in the sense that it's got heaps of steps to it, but it only uses NCEA level 3 maths just repetitively, and if you be careful with your maths, we'll get here. The other thing to note is that this last question, part B, was worth 3 marks. So it's worthwhile getting it correct and being careful. So we have this function here, and we need to differentiate it 3 times and find the values of k for which the third derivative is just equal to some constant times the original function. Okay. E to the minus x sine kx. Okay, let's differentiate. Once, we need the product rule. So we've got f, and we've got g, and we want f dash g plus g dash f. So f dash is negative e to the minus x times g, and then g dash is sine of kx, so it differentiates to cosine of kx times k multiplied by the first function. Okay, so that's the first derivative. Now, if we don't spot patterns, it's going to be real tedious. We want to find the second derivative. Let's look at the patterning first. We've got this function that we started here with. It's actually appeared again, but just with a minus in the front of it. So when we differentiate this term, we're going to get the whole derivative again, just with a minus. So the first part differentiated, it's going to go back to e to the minus x sine kx minus k cos kx e to the minus x. That's the first term differentiated. And now the second term differentiated, this is going to be u, and this is going to be v. And I want u dash v plus v dash u. U differentiated is, or cosine differentiates to minus sine, so it's, and we're going to get another factor of k in there. So we're going to get minus k squared sine kx times e to the minus x, and then v dash is going to be minus e to the minus x times k cos kx. Okay, now there are some like terms here, so before I differentiate it a third time, I do want to tidy them up. We can see here that there's an e to the minus x sine kx there, and there's also e to the minus x sine kx there. So putting those together, we've got 1 minus k squared e to the minus x sine kx. And then the other terms that are like terms, e to the minus x cos kx. We've got minus k, and we've got another minus k, so minus 2k e to the minus x cos kx. Okay, so that's the second derivative. Now we need the third derivative, but the original functions appeared again. So it actually might have been useful in this to use implicit differentiation and then call this whole thing in yellow equal to y. And then we're going to have dy dx appearing and d squared y over dx squared appearing. So you might want to explore that if you're good with implicit differentiation. But what I'm going to do, just to continue in the same vein, third derivative, this whole first term here is just a multiple of the thing we started with. And when we differentiated that thing right at the start, we got the two terms in the second line, dy dx. So this part, when we differentiate this first part, we're just going to get that multiple, 1 minus k squared, all times by the first derivative. Okay, so I've just taken that first derivative in line 2 and multiplied the whole thing by 1 minus k squared, and that diffs the first term in the second derivative. And now I need to differentiate the last term, but that is just minus 2 times the second term in the first derivative. I'm running out of colours for highlighters. I hope you're following this, but we've got this dude here, which appears there. We've just got a minus 2 in front of it. So when we diff it, we're just going to get minus 2 lots of the last two terms in that. Okay, so minus 2 lots of negative k squared sine kx e to the minus x minus e to the minus x k cos kx. Okay, I'm going to explore the implicit one in a sec. Actually, I think it might be nicer. Now we've got to put this all together somehow and collect some like terms. So do the same thing as what I did earlier with the pink stuff. We've got e to the minus x sine kx there, and we've also got it there. So those like terms go together. Be careful with the expanding of brackets. And in the cos kx terms, go back to my green highlighter, that term there and that term there. Okay, and the goal in this question, remember, was to make this equal to c times y. C times y. Find the values of k for which this is true. Well, the y function, which was the thing in yellow right at the start, is just this dude here. So if this is going to be equal to c times y for all values of x, then this last term, well, that has to be 0. Okay, if this is here is equal to y, this will be equal to c. And for that second term to be equal to 0, well, for all values of x, we actually need to consider the coefficient of it. The reason for considering the coefficient is e to the minus x is never 0. This cosine kx term is equal to 0 for some values of x, but we want it to be true for all values of x, so we set the coefficient equal to 0. Therefore, this dude must equal 0. And to solve that equal to 0, what type of equation we've got? We've got a cubic equation. Let's just check before I do that I've got the right stuff. Oh yeah, but there's a common factor of k, so that's all good. K is not equal to 0. Okay, if k was equal to 0 in the original function, we would get sine of 0. We would get a y value of 0. So hey, if a function's 0, then its first, second, and third derivative are all 0, which is some multiple of the original function 0. So we're excluding that case, and we're just saying, therefore, k squared must equal 3. K is plus or minus square root 3. Now for that k value, k is plus or minus square root 3, we go back to the c value, and we work out that what the c value is. C is equal to minus 1 minus k squared plus 2k squared, which is equal to minus 1 plus 3k squared. If we sub in k squared equals 3, we get 9 minus 1 is 8. Okay, so that's the answer to the question. Now for this last little bit of the video, I'm going to just explore using implicit differentiation to do this, so that we we can use the repetitive nature of it without getting all these specific functions. Okay, a similar but different way of doing this problem is if we start off with y equals minus e to the minus x sine kx, and rather than use product rule, we could use logs. So if we log both sides using the natural log, we can turn the product into a sum. So log of y simplifies to ln of e to the minus x, which is minus x, plus ln of sine of kx. And then I can use implicit differentiation on this. So a differing log of something gives me 1 over something times the something differentiated. So that left-hand side diffs to 1 over y dy dx. The right-hand side diffs to minus 1. And then the log of sine of kx differentiates to 1 over sine kx multiplied by the derivative of that, which is k cos kx. Now if I times the whole thing through here by y, I get dy dx is equal to negative y, and then the y, remember, is e to the minus x sine kx, so timesing through by y, I'll lose the sine kx in the denominator of that last term, and I'm going to get plus k e to the minus x cos kx. So essentially what I've shown here is that the thing you started with appears again in the first derivative. And so it's a repetitive thing. But we get this with other term, e to the minus x cos kx. So on the side of this, I'm going to call this whole thing here equal to u. So if I've got u is equal to e to the minus x cos kx, using a similar approach by logging both sides, and then turning it into a sum, diffing implicitly, and then multiplying through by u, the cosine kx's will cancel, and then realizing again that the y thing turns up in here because of the fact that sine and cosine alternate when we're differentiating. Okay, so going back to, we've got the first derivative. We now want the second derivative. We can just do this all implicitly. D squared y over dx squared. Okay, diffing the first term, minus y diffs to minus dy dx. And the second term, well, diffing that is going to be k times du dx. And then realizing that, well, actually du dx, we've already seen that term, it's minus u minus ky, so we can rewrite this. And we've actually already seen dy dx, so actually I'll make a bit of room here. Dy dx was equal to minus y plus ku. It's going from the line above it. So this equals y. We've got some like terms. So first term is y, and then there's another y that comes later as a minus k squared. So we've got 1 minus k squared y. And then we've got some u's as well. We've got minus ku, and then another minus ku, minus 2ku. So there's the second derivative. And now the third derivative, d cubed y over dx cubed. Well, the constant just stays there. Y differentiates to dy dx. Minus 2k just stays there. U differentiates to du dx. And And then we do the same thing, we replace the expressions like I did earlier when I had a dy dx. I replaced the expression, and when I had a du dx, I replaced the expression. So dy dx is equal to minus y plus ku, and du dx is equal to minus u minus ky. Why am I doing this? I'm trying to get it into a form c times y. So wherever there's derivatives, I want to replace the derivatives with multiples of the original function y. And then we've got some like terms again. We've got 1 minus k squared times negative y. And then later on we've got minus 2k times negative ky. So that's going to give us 2k squared plus another k squared. We're going to get 3k squared minus 1 all times y. And then we've got some u's. We've got 1 minus k squared all times ku. And later on we've got minus 2k times negative u. So we've got 2ku plus another ku, so 3k minus k cubed all times u. Now remember that y is just a function of, well, a product of two functions, and so was u. Okay, y was the yellow thing at the top here, so, and then u is the green one. So they're two functions, but we want this third derivative here to equal c times y. So it follows a similar conclusion as the first method, in that functions are only equal to 0 at a set number of points. If it's going to be 0 for all values, then we set the coefficient equal to 0. So we go 3k must equal k cubed. K is not 0 for the same logic as earlier, so k squared must equal 3. And then if k squared equals 3, or k is plus or minus root 3, and then we chuck it up into the coefficient here, 3k squared minus 1, we get c must equal 8. So this method here, I didn't use specific functions past the first derivative, because I just kept relating the first derivative in terms of the previous function that I'd already seen. Second derivative, I just replaced the derivatives and reduced it down every time, and that made the stuff easier to work with, but it did introduce a few more letters. It introduced the u, for example. So hopefully that method showed you another way of solving it and you liked it, but I guess the trick of using logs to turn products into sums is quite nice, because when you get horrendous functions that you want to differentiate, the product rule isn't the best way to go about it. And same with quotients. The log of a quotient turns it into a difference of two functions, which can be easily navigated. Catch you in the next one.